These are notes on chemical equilibrium, specifically something called Keq and Q. And so I'll get into what those are in a minute. Those are in 18.2 in your book. One thing to note is Keq is in your book, but Q is not. So that's a topic that the National Science Standards say you should know, but is not actually in your book. So just kind of keep that in mind. So Keq is an equilibrium constant. So K, we're used to being a constant. If you remember back to the gas laws, we said like PV, pressure times volume, equals K is a constant. So K stands for constant, and then EQ obviously is equilibrium. So this is an equilibrium constant. It is a numeric value that we place on a system in equilibrium. And in talking to Mr. Lockett, he really introduces this concept at the beginning because then he feels like understanding this concept helps you better understand equilibrium. I like doing it a little later because I want you to understand the concepts surrounding equilibrium before I just throw in a number. Because those of you who are very numeric are going to gravitate towards this number. And as a lot of you know, you can reason through numbers without actually understanding what you're talking about. So that's why I chose to save this part, but I think some of the questions you guys have had may be explained through understanding the equilibrium constant. So as we said, Keq is expressing equilibrium as a numeric value. And what it does is it relates the concentration of the reactants to the concentration of the products at equilibrium. And I found out today in class that a lot of you are fuzzy on this idea of concentration. So remember that concentration is the amount per volume. So often, especially when we're talking about gases and liquids, we're talking about moles per liter or molarity. That's a concentration. So a concentration is a certain amount of stuff per a certain volume, in a certain volume. So in your Le Chatelier homework where it'll say, you know, what if you decrease the concentration of whatever NO2 gas? The way you would decrease it is remove some of the NO2. Then you have less amount in the same volume, okay? And the way this works is Keq and this, let me get the pen here, this symbol here, the brackets, that is the symbol for concentration. So this means the concentration of the products divided by the concentration of the reactants. That's what this symbol means. So let's make this even more detailed. If I have this reaction where the capital letters A, B, C, and D are my compounds, and the lowercase letters A, B, C, and D are my moles, so I have A moles of capital A, B moles of capital B, yielding C moles of capital C, and D moles of capital D. This would be like a double displacement reaction, maybe. Then, and by the way, this big A, big B, little b thing, this is actually how, like if you go on to take chemistry at college or an AP, this is not me making this up. This is actually how they note this, which for some of you is annoying because you're like, why are there so many A's and B's? And others of you will find it quite seamless. So Keq, remember we said products divided by reactants, is the concentration of C, capital C, raised to the power of lowercase c, times D raised to the power of lowercase d, so whatever the concentration of D is to the power of the number of moles, divided by A to the A and B to the B. A couple things to know. I will always give you problems dealing with gas. It's slightly different dealing with liquids and solids, and if you're looking for kind of the extra credit that will be on your test, you're going to want to find out why it's different for liquids and solids and how it's different for liquids and solids. So you're going to, just so you know, you're going to need to know both the why and the how if you want extra credit on the next test. And Keq, just to let you know, is temperature dependent. So for any reaction, as you're removing something or adding something or changing the volume, as long as you're not changing the temperature, Keq will remain the same at that constant temperature. If you increase or decrease the temperature, the value of Keq actually changes. take a second, kind of think through that. There's a lot here. This part is in your book. So let's talk about what Keq actually means. The value of Keq compared to the number 1, the value 1, can be used to determine whether in your equilibrium reaction more products or more reactants are created. So if you go back to the beakers and the straw activity, you know that at equilibrium we had more products than reactants, and we say that that is a product-favored reaction because you actually had more product than reactant. Some reactions you end up with more reactant than product. It doesn't seem to react a lot. Some you have so much more product than reactant, you almost can't tell the reactants are there, and the reverse. Some you have so much more reactants than products at equilibrium that it almost appears like it didn't react at all. And you can compare Keq to 1 to determine whether there are more products or reactants. So let's look again at this general equation, products over reactants. So if Keq is 1, that would mean this, the concentrations here, is exactly equal to the concentrations here, which would give you a value of 1, right? It would have to be something divided by the exact same thing, meaning identical concentrations. So you'd have the same amounts. But if Keq is greater than 1, that's going to mean that this, the products, is larger than the reactants. This has got to be small, okay? So sorry, that was supposed to be a big arrow. So a large number divided by a small number is going to give you a number greater than 1, which would mean the products are favored because that number would have to be really large. Okay, let's erase that. Similarly, if Keq is less than 1, that means that is a reactants favored equation at equilibrium, because then this number's got to be really high to get a number less than 1, and this number's got to be lower. So more reactants than products to give you a decimal number. So now let's look at the reaction quotient, which is Q. And this, as I said, is not in your book, but it is part of the National Science Standards. So we want to make sure that you understand what's going on here. Q relates the concentrations of the reactants and products anytime, whether it's at equilibrium or not. So remember, when you're first starting out, there's going to be all reactants and no products, and then those you slowly decrease your reactants and increase your products. If you remember that graph from the previous notes on Le Chatelier, sort of a graph, here I'll draw it here, that looks like this and like this. And at some point, maybe here, that's where you reach equilibrium. But, you know, there are concentrations of reactants and products here as well. They're just not stable. So Q looks at the concentrations at any point in time during the reaction process. And it's calculated the exact same way as Keq, because what we're going to use it for is looking at how it's going to shift the equilibrium or the reaction. So exact same way to calculate Q as Keq. Okay, so now I want to talk really briefly about what it means to shift the equilibrium. So again, this was something that came up today where I realized people are using this term and they really don't know what it means. Remember that at equilibrium, the rates of the forward and the reverse reaction are equal. So if you do something to throw off the equilibrium, you increase the volume, you add some heat, you take away some heat, you decrease the temperature. You take away a product or you add a product, something like that, or add amounts of products. I shouldn't say add a product. That makes it sound like you're adding a new compound, but you add more of a product that you already have. That's going to shift the equilibrium. What that means is that after you've applied the stress, it will favor, remember these reactions at equilibrium are at the same rate, but once you add that stress, one of the reactions, either the forward or reverse, will speed up to compensate for that stress until the reactions are equal again, equal rates. So let's look here at these concentrations, okay? Let's say, and let's go back to the beakers quickly here we have our beakers, and at equilibrium, those aren't quite the same size, but whatever, we had this much in one and this much in our products beaker. Now, and the rates were the same. Now, if I pull out some of this and give it a new level, can I give different colors? Maybe I can't. All right, but let's say I give it a new level. I go to there. Now, here well, I'm going to leave that. Now, the reaction in reverse is going to slow down, right? Because now I can't get as much water in the straw, meaning it's going to be slower than the reaction going this way. So this reaction will slow until I've transferred enough water to reestablish that equilibrium, and it'll reestablish probably somewhere around there. And this will be a little lower. Okay, so I didn't give myself quite enough room. But that will be a new ratio, or it'll be the same ratio but with new amounts because I've removed some of the liquid. So that's what it means to shift the reaction. So if I remove some of the liquid from here, it's going to shift the reaction that way, meaning the forward reaction now will be faster than the reverse reaction until you reach equilibrium again. All right, so let's look at what happens if Q here, let's go back to Q and Keq. If Q is greater than Keq, okay, Keq is the concentrations at equilibrium. If Q is greater than Keq, that means the reactants have been favored in this reaction. So think about this. In order for Q to be, or I'm sorry, the reactants will be favored. In order for Q to be bigger than Keq, that means this number here, the products, either need to be larger, or this number here need to be smaller. That's what's going to give you a larger Q than Keq. And so, because of that, you want to, what the equilibrium will do, not you, but in order to get to equilibrium, you're going to want this number to drop and this number to rise so that Q drops since it's bigger than Keq. So that means the reactants are going to be favored, meaning the reaction will go to the left, meaning that reverse reaction will be faster than the forward reaction. Similarly, if Q is less than Keq, then that's going to be a products favored reaction, and it's going to shift the equilibrium to the right, or the forward reaction will be faster than the reverse reaction because, let's go back to here, if Q is less than Keq, that means this number here is too big, or this number here is too small. Either way, in order to get them to be equal, at equilibrium, Q, let's actually write that in. I don't have this in, but at equilibrium, Q equals Keq. I'm not going to try to write at equilibrium, but you can write that. At equilibrium, Q equals Keq. So in order to get these to equal one another, if Q is less, you would need this to decrease and this to increase because it's a reaction, right? Go back to the beakers. As one decreases, the other increases. They can't both increase or both decrease at the same time. So that's going to favor the products. It's going to shift the equilibrium to the right. The forward reaction will be faster than the reverse. All right, let's look at some examples. So here we have an equation, 2SO2 plus O2 forms 2SO3. This was the reaction we've been working with. So the equilibrium concentrations of the above reaction are listed below. So SO2 is 0.76 molar, O2 is 0.907 molar, SO3 is 0.835 molar. What's the Keq of the above reaction? So go ahead, pause the video, calculate it, and then check your work. So you should have gotten this equation. Okay, now in this case, there is no D, right? We only have one product here. So it's 0.835 squared. The squared comes from this number of moles here. And then divided by 0.76 squared, so 0.76 is here, squared, times 0.907. That's this concentration here, and that ends up being 1.33. There are no units because the molarities will cancel out. And so is this reaction going to shift towards the reactants or towards the products? I'm sorry, that's not the question. Sorry, that's dealing with Q. The question is, does this reaction favor the reactants or the products? So this is a slight favor of the products. It's really close to 1, and so they're pretty equal as far as the concentrations, but because this is more than 1, we know this number here has to be greater than this number there, so that's a slight favor of products. And you can get KEQs that are like 1 million, or KEQs that are like 1 millionth, like times 10 to the negative 7 or whatever. So, you know, these are nice numbers that you understand, but you can have KEQs that are incredibly extreme, and so that would be a huge favoring of products or reactants. So let's look at this reaction, which we've seen before as well. N2O4 gas reacts to form 2NO2 gas. So 2 questions here. So the KEQ value for the above reaction is 0.300. Solve for the reaction quotient, so that's Q, you can think quotient Q, when there are 2.15 molar, so 2.15 moles per liter of N2O4 and 4.33 moles per liter of NO2. So this is saying this is not necessarily at equilibrium. So here are the concentrations you happen to have. So you come across this beaker and you get these concentrations. What's the reaction quotient? And then, based on that, which way will the reaction shift? So go ahead, pause the video, solve the problem, see what you get. So for Q, again, here's our equation. Now, in this case, we don't have a D or a B. And certainly, if you had 3 or more reactants or products, you can just continue that out. So it's basically the concentration raised to the power of the coefficient. So here we've got 4.33 squared. So the squared comes from here. Here's our 4.33 divided by 2.15. I mean, obviously raised to the first power. You can certainly put that in there if you like a placekeeping. And that's 8.72. So now what we see, obviously, is 8.72 is greater, much greater than 0.3. So let's get a nice, there we go. So how's that reaction going to proceed? How's that reaction going to shift? Remember that our goal is that we would get Q to equal 0.3. So we want to reduce this number. So how are you going to reduce this number based on this equation? Hopefully you got that the reaction will shift to the left. That in order to get this number lower, this number's got to be bigger, and this number's got to be lower. So this reaction is going to shift to the left, meaning the reverse reaction will be faster than the forward reaction until you reach equilibrium. And by the way, if you don't know, these 3 dots are the mathematical symbol for therefore. So Q is greater than KEQ, therefore the reaction will shift left. These are things you can memorize, but it's much better if you understand why they are the way they are, which is why I didn't introduce numbers right away. Finally, we've got H2 gas plus I2 gas forms 2HI gas. And so the question is solve for the KEQ when the reaction above when the gases are in a 3-liter container with this many moles of H2, this many moles of I2, and this many moles of HI. Go ahead and pause that and try to solve, and then check your answer. So the first step is you actually have to calculate concentrations. We don't know the concentrations here. We have moles. So we have amounts, we have volume, we have liters, so we have to find the concentrations. So the concentration for HI is the 1.09 moles divided by the 3-liter container. The same thing, I2 is 3.1 moles here divided by the 3.0 liter container. Here for H2 it's 5.64 moles divided by the, oh, these should actually all say moles. I'm noticing that now, not molar. So that should be MOL. Okay, and that's actually all the way across. There we go, because then that makes molar solution. Now we have our concentrations, so we can plug them into our equation. And we have 0.36 squared, so the 0.36 comes from here, it's squared is there, divided by 1.0, that's here, times 1.88, that's there, and that ends up being 0.069. So this is a reactants favored reaction, because here, so this reaction is not going to proceed very far away. I mean, it's not bad, but clearly it's not going to proceed very far away from the reactants, or this number wouldn't be less than 1. So meaning this number is bigger than this number. Please feel free to put any questions you have on the comment section of YouTube or ask them in class. Have a good night.